Okay, the reductive dechlorination reaction is an important one for remediating chlorinated compounds. It can be done in situ in some cases, and it's responsible for degrading PCE along this chain to ethene. The kinetics of this reaction from PC through VC, not really, there's one more step here that's not shown, but this is from a paper by Yu and Semprini. And so what we're going to do is write a simulation that uses these kinetics. And at first glance, there's a lot going on here. This is fairly complicated. But we've already seen all of the components of how to do this analysis. So what I'm going to do is take a look at it in a little bit larger format and compare it to some of the other things that we've already seen. So here's the Monod equation, and it says that the rate is equal to this guy, constant times the dependent variable, pair of constants here. There's the dependent variable, another constant. These i's are the inhibition terms. And sometimes when we first saw the Monod equation, these i's were left off, but I put them in there to include inhibition. So this is all Monod kinetics. That's what's going on here. If we look at the PCE equation, we can see it. There's K max is K1, and in this case, the dependent variable is CPCE. So there's CPCE, there's that. And this is X is the microbial population, and so we would need to include that up here to match this equation. Down in the denominator, a constant that corresponds to K2, and CPCE, which is SS. Okay, so there's no inhibition in this one, but there is in the next one. This is the degradation of TCE, and this is just another Monod equation. You can see up here, this is pretty much all the same except we swapped TCE for PCE. And then down the denominator, we've got these terms here in parentheses, which are the inhibition terms, what I'm calling IC and IH. IC is just 1 plus the concentration of PC divided by that thing, which is a constant. And so this is the degradation of TC by Monod equation or Monod kinetics, and then this is the production of TCE from the degradation of PCE. And if we compare this expression to this one, we see that they're identical. It's just the sign has changed. Okay, so we're starting a decay chain, and if we recall from the decay chain that we've already worked on, this is the first order decay chain, and the way it works is that the kinetics here, this is the degradation of A, and then B has a degradation term and a production term. And C has a degradation that's first order in C and a production term related to the degradation of B. Basically, it's just that term right there with the sign change. Well, this is doing the same thing. This term here is similar to this one. The degradation of TCE, the production of TCE by the degradation of PCE. Here, this is cis DCE, and it's being degraded by this Monod equation. It's just the same, exactly the same as this one, except the subscripts have been changed. So these are constants, but these are different constants, and this is the dependent variable, and of course it's different. Okay, so that's all we have here is a decay chain, very much like what we've already solved. Okay, so I've set this up in COMSOL, and let me show you how. So here's the model, and we'll first, I guess, let's look at this equation. So this is the Monod equation done as an analytic function. And I think this was used in one of the examples that you did for homework. What I added here, though, was this term X. It's the microbial population, which for our problem here will just hold constant. And so we can call this by using this term monad and having this set of parameters that we pass into it. I set up a list of variables here, and so there are a bunch of constants that are used in this analysis. Each one of these monad equations has, I guess, 4 different constants. So it has a constant Kmax, and a constant Ks, and a constant Kc, and a constant Kh, all for each one of the species. And so these numbers here are given by Yu and Semprini in Table 2. So I just simply came up with a convention for naming the variables so I could look at the variable name and tell what it was, and then just wrote down the numbers here that Yu and Semprini have in their table. Okay, so the next step was to write out the decay functions. So I did it really in 2 steps. I first wrote out the decay function, which is just the monad equation, and then the reaction that includes both decay and production. I wrote that using these 4 different terms. Okay, so here's how it works. The monad, it's negative, and then I'm passing in the variables, the Kmax and Ks variables. PCE, that's the dependent variable. X is the microbial population, microbial concentration. And then these 2 guys are just equal to 1. These are the inhibition constants. And so let's take a look at TCE. It's pretty much the same here, except it differs when we get to this term. So that right there, that 1 plus CPCE divided by KCTCE, that's the inhibition term that, let's see, we saw it over here. That's that inhibition term right there. Okay, so we've got another inhibition term here. And one of the things you just have to keep in mind is this first inhibition term, it depends on the concentration of the compound in the decay chain above it. So this is the expression for TCE, and it depends on the concentration of PCE right there. Whereas this Haldane inhibition, it depends on the concentration of TCE. Okay, so the rest of these terms are the same, except you just change the TCE and DCE and DC. Okay, so wrote that out, and then this is really just the 2 terms. The one for TCE, the reaction is the decay of TCE and the production of TCE by the degradation of PCE, and so that's why there are 2 terms. And we take that on down to ethene. So those are the reactions. Then we set it up. Really, this part is all the same as what you've seen. In this case, there are 5 dependent variables, and I guess it would be worthwhile. Let's take a look here. So there are 5 dependent variables, and for some reason it's kind of hard to see all 5 the way they've set this up. It's not really designed very well, but nevertheless we can verify. I call them C underscore PCE, and we can see that those variables are used right there. So that's the dependent variable that I defined right here. And then if we go to initial values, what I'm doing is starting off with an initial value of 1,000, in this case moles per cubic meter, and no concentration for the other compounds. And the reactions, I've already written the reactions out up here in the variables, so I just type the names of the reactions that I've given it. And it's a default mesh. And so we're ready to go. And this one runs fairly quickly. And we should have some results here. So here are the results. PCE, it drops pretty quickly. Oh, and I ran this over 10 to the 6th seconds. So this is about 12 days, something like that. And if you look in the paper, they have experiments that last about that long. And so PC is dropping quite quickly. And TCE, I guess this is TCE, it increases and drops off. And then DCE, and then vinyl chloride gets to be quite large, and it hits the spike and comes down. And then this is ethene. And so if you look at the figure, that's I guess figure 1 or figure 2, you'll see that the curves look pretty much like this. And so this is a fairly state-of-the-art analysis of the decay kinetics for PCE, and we've implemented here in this code. Now we're really just implementing it in a fairly simple way, where we have this square block and the concentrations are uniform here, but we're just getting started here, right? We've got this fairly complicated set of chemical reactions that we've implemented, and now we can start to consider moving on and adding in flow and other processes to see how they interact.